had an object that I wanted to destroy. I tried breaking it in a vise, it didn't work. So I used a hammer. There are different materials and they all have material properties. Often you can find these online as a technical data sheet. There are physical, thermal, and mechanical properties. There's also chemical resistance. There's a mechanical property called Izod impact strength. The Izod impact strength is an impact strength testing procedure credited to Edwin Gilbert Izod. There's a test specimen which gets struck by a hammer pendulum of sorts.
I got interested in impact strength after I got a new material and I had brought a 3D print to school, and it was really hard to break until my friend stomped on it and it shattered into a million pieces. And I'm like, oh man, that's the impact strength. Impact strength tests are testing how much of an impact a material can take. An impact is a large force applied over a short period of time, like the hammer. The test conditions are controlled by many variables. There's the mass of the striker, the height at the starting point, the temperature, and specimen dimensions. I'm going to have specimens based on an online image. To get a better understanding of impact strength, I decided to make an impact strength tester and try it out. Here we have a pendulum. It's almost at the top of the swing. Let's pretend this is like my pendulum. So basically, at the top of the swing, it's almost all potential energy. So here's the point of rotation, and then there's like the point, and then potential energy equals mass times gravity times height. And that's basically how you calculate potential energy, which we already learned in class. So after a bit, it's going to reach the bottom of the swing, where it's all kinetic energy, because it has no more potential to swing farther down. And now the rest of the kinetic energy is going to be used to swing up in the other direction. In a perfect world, it would, not a perfect world, in a perfect vacuum, I believe, the pendulum can swing infinitely, I guess. And so it traveled this height, and the kinetic energy equals 1/2 mv squared. And that height is going to be h. So after you simplify those two equations, like the kinetic energy and the potential energy, as we learned, the velocity at the bottom of the swing will become square root of 2gh. So after that, we can plug that square root of 2gh back into the kinetic energy equation, replace the velocity with square root of 2gh, and then the square root gets canceled out by the square from v squared in the kinetic energy equation. So the mass, the units, is in kilograms, and I have calculated the mass of my pendulum to 0.76 kilograms. And then the 2 is just 2. The g is in meters per second, so meters per second. The g is in meters per second. And the height is in meters. So basically, and then after I plug this into a calculator, the kinetic energy is in joules. In my output, I get kinetic energy at the bottom of the swing. I get 2.840 and some other numbers, which I'm only going to talk for calculations. So basically, and then that's the amount of energy at the bottom of the swing. So when the impact test sample gets struck by the pendulum, let's just say there was like a broken piece of thing here, so this is right here, and it just got blown off by the pendulum. It absorbed a little bit of impact from it being a solid piece of like plastic in my case, and that will show how much it swings back up on the other side. So in my build, I have a dial, and it pushes it up, and it will only stay at the peak of its swing on the other side. And that way I have a piece of paper here, and it will show me how many degrees it swung to, and then I'm able to see how much of an impact that the piece of plastic absorbed in joules. So then after that, the cross-sectional area of the impact place is also important, as the result is joules over meters squared that is absorbed. And all of the specimens, they have 0.0000508 meters squared, which is not like small space, because the specimens aren't huge, like in meters, right? So after that, I can take the amount absorbed. For example, Eastman amorphous polymer, it absorbed 0.12624.816 joules, and basically after I divide it, I get like a lot more joules than like not even a joule. So after I divide it, I get 2485.2 joules per meter squared. meters squared. And basically, then you can simplify this into kilojoules, which is 1,000 joules. Alright, time to test out some specimens on my new testing machine. Yeah, that was just wondering even break. Currently, with the heat in my house, I'm unable to get perfectly accurate test results as the temperature I cannot regulate in my garage that well. Knowing material properties is important because you can predict how a material will behave and like what material you should use for the job. Like on a bridge, you would want like bridge materials, or else like if you use like wood or like paper, it might break, right? There are so many different material properties. My measurements aren't perfectly accurate as the temperature and how I release the hammer is also another part that I could have improved on, where like releasing it from a set point instead of basically moving it to 90 degrees from eyeballing it.